All right.
Professor, you're muted.
Right. Yes. All right. Thank you. Yes, I was totally muted. Thank you. So I didn't hear. So hello. Yes. Hello. Okay. Let's do hello. Yes. Hello. Hello, Rahel. Hello, Kat. Sorry. Wait. Did I? Yes. Hello, Rahel. Hello, Soha. Hello, Johandri. Hello, Gabrielle. Hello, Harry. And again, correct my pronunciation, please, when applicable. Hello. Hi, Jasmine. Hello, Vanietta. Hello, Jesse. Hi, Skyla. Awesome, awesome. Oh, and there's more people. Sorry. Wait, more coming. Blah, blah, blah. Okay. Oh, and hello, Michaela. Michaela. Sorry. Michaela. Well, you'll have to correct me, please. Wait, who else we got? Kat, Rachel, Iola, Jasmine, Jesse, Johandri. Ah, That's very kind of you. You're definitely going to be seeing him. Believe me. I mean, this is a long. Oh boy, you'll be. Yes, I mean, for good or for bad. And I'll tell you what. Like, you don't understand. This class in particular. Every day he wants me to text you, all of you guys, or put in Google Classroom something about he's desperate for this Mewtwo in Let's Go. I mean, it's crazy. Yeah, you'll see him. Believe me. Well, that's well. When believe me, just when. Well, anyway, that's very well. He'll just when I get momentum, he'll come in. I'm sure. But anyway, all right. So hello. So we say hello, Kat. We say hello, Rachel, Iola, Jasmine, Jesse, Johandri, Gabrielle, Skyla, Vanieta, Michaela. Sorry, Rahele. Um, Har- huh. We'll come back to those two. God, right. So, hello, and on hell or on, sorry, Angel. Say I forget if it's. You'll have to tell me if it's Angel or on hell. And Melanie, hello. Okay, and chat. Okay, this is
It's
good.
Angel, Professor.
Oh, sorry. What say?
You could say Angel.
Okay, why do I? Okay, thank you. I appreciate it. I don't know why I do that every time. All right, thank you. Oh, and there's more people to save me.
No problem.
Okay, thank you. And devil backwards is lived. You know what I'm saying? And evil backwards is live. So I don't know what that has to do. All right, quasi. I mean, and okay, so people are coming. All right. Oh, and yet another. Wait, this is a big class. Okay. Now we're gonna get. Oh, and Skyla, hello. Or did I say that? Well, everybody, hello. Okay, we're gonna get to business in a second. We're gonna get to hello. Thank you. Hello. We're going to get rolling. We will be interrupted. I'll try again to either give a quick break in the middle or let us go a little early. Like it's a lot, to go straight. And obviously, we'll try to mix it up. But one thing before I forget, yes, before I forget, I think you're all in a very good place with. Like, I like this class a lot. Again, and believe me, it's not that I don't say that every semester. Some semesters I don't say anything at all. And quite frankly, if Walters hasn't mentioned it, last semester we were not going around saying how much we like the class, this class. So we think you guys are doing great. I know we both feel that way. Yeah, yeah, right. No, it's true though, really. And we think you guys are doing great. And many of you turned in homework 3, which is impressive. And some of you even pointed out that it was kind of hard, or it was kind of a leap from where we were in the class, or felt like a leap, or a leap from how you feel comfortable or don't with math, all which is fair. Like it was. Like anybody who did homework 3, even if they didn't do very well at it, did very well, if that makes any sense. I was very impressed. Like it was an undertaking. It required some more like thought on your part. So, but a lot of people rocked it anyway, in either sense of the word. If you have not done homework 3, you're not late, no problem, because today will clarify things, hopefully somewhat. You'll understand it better, so you could still hand it in. I also want to say to everybody, just to continue the message on any, like these homework points do pile up, like they're to your advantage. You can never be punished by anything wrong on homework or in those participation things. All the points are, just to your advantage. But one thing to be clear, again, especially because I think people are doing well and there's no reason not to continue. If you ever get first of all, if you've done any homework in this class, for me, I think you've gotten it. I hope you've gotten it back. Like, unless you turned in something today, I haven't looked. But as of last night, I think anything and everything that any one of you has turned in of any kind to me, I hope you got back. Let me know if wrong. Again, if you turn in something today, then that's fine. It's not past any deadline, but like I haven't gotten to it yet. But what I'm trying to say is this: if you ever got anything back on any homework or anything that's less than a 50, please understand again, whatever I put in the comments or something, less than a 50 is not a punishment, and it's not a axe falling, it's like you still could do something to make it a 50 if you want. Sometimes it's not worth it. It may often not be worth it. But if you feel it is, you can always, if often I'll say for full 50 points, please submit a more thorough solution to blah or something. Whatever it is, there's always something you can do. So none of these grades are static. I mean, like revision is to be rewarded. Okay. So no one's behind or anything. People could still hand in homework 1. People could still, that I might be a little bit twitchy about. I mean, about giving full 50 points, but whatever. Homework 2. Sorry. I keep saying homework 3. No, I just realized. I'm sorry. The homework that I'm talking about is homework 2. I just realized. Sorry. The homework that's a little bit hard, that was most recently put in your box, that many of you have done, but many of you not. That I mean homework 2. There is no homework 3 yet. Sorry, I just realized. That's probably in the chat. I'm gonna look at the chat right now. Yeah. Right. Okay, sorry. Yeah, totally. I mean 2. And I promise I didn't even know that until I just looked right now. But yeah, I mean number 2. Everything I just said is about number 2. That's correct. There probably will be a homework 3 soon, but you haven't heard about it yet. Okay, wait. That's that. And someone's here. That said, so we will start going over. Oh yeah, especially because I know we didn't even technically necessarily say everything there was to say to finish going over homework 1. Like I'm aware of that. But even if all that's true, I believe before I get into any homeworks or anything, again, since I'm just saying like grade wise, I think we're all good. This is that delicate, dangerously part of the show where I find out from you what just happened with you guys in Walters. And let me say again, I'm hoping that these sessions, when you bring me up to speed and then I try to clarify what I think is the point, hopefully that means that you feel that both your classes are talking to each other. And hopefully it's clarifying. If you ever feel like you've done something in Walters and then I start talking about it and I'm muddying the waters, and I mean this, if ever you feel like you did something in Walters and it was clear, but now the more I'm talking about it, it's starting to get less clear or something, you've got to stop me and let me know, because that is definitely not the goal, but it could happen. So that said, I turn it to you guys. What's motion 4, or what did you do? And you can screen, you can share screens, whatever, but what's your feeling about what you've now learned in motion 4 with him? Or, okay, I'm looking. I see the chat. Okay. Oh, cool. He did that. Oh, that's okay. Oops, sorry. So just. But even if I'm responding, don't like. That's a good. But still, other people still weigh in. It's not a race. And if you guys have different ways of putting it, or you have different experiences, it'll help me to see different. So that's a good answer. That does help me, but it doesn't have to be the only answer in the chat. But it does sound like you didn't get a new motion. Am I right about that? You did not get a new motion. Then I should change. You analyze. Oh yeah, the carrot thing, right? Okay, and you analyze it qualitative and quantitative. That's very cool. So am I right to infer from this that actually, and that's great if it's true, but does that mean that you didn't get a new motion, like you're practicing understanding what to? Oh, we did. Okay, cool. Yes, I think you're right. And you is cat. But this is very good, because it sounds to me what you're saying. This is very helpful. And we're gonna stay on this for. I mean, and actually, this sounds like. Oh, actually, it really sounds like you were. It sounds like things are working very well, because if I'm understanding correctly, it sounds like you were experimentally playing with exactly the idea that I was trying to pound at the week before, which is, I mean, if I understand correctly, if you were testing whether things were really harmonic or not, presumably what you were testing qualitatively and quantitatively was whether they maintained some kind of frequency or some kind of tick rate, some kind of period or frequency that remained constant no matter what you did to the amplitude or whatever, regardless of what happened to the amplitude. I mean, is that a fair summary of what you were? And yeah, and I'm willing to totally believe what Kat is saying here. I bet there was a new equation, which we'll write down in a second, but a new way of saying harmonic oscillation, but probably not an actual new motion, like not a new concept, but a new way of writing. I mean, in other words, I don't think we're up to motion 4. It sounds like from a, I'm checking with you guys. I mean, this is what I'm understanding you to be telling me. Is that like, wait, well, for one thing, do you have something like this? Well, wait. When you say you do something like this, I'll give you options. Either this or this, or something like, do you mean something like, is it something like one of these? Or if not, tell me, whatever equation you were talking about, I definitely want to know whether it's a new motion or not. Was it one of these or something else? Option one. Okay. This is very important to help option one. Okay. Like, so you, okay. Right. So you didn't have a cosine thing. So, but, and am I right that, I mean, I don't want to, did he call this motion 4 or no? Like this was like a new way of looking at simple harmonic oscillation, which is still motion 3. Does that sound fair? Or did he actually call it motion 4?
It's called motion 4 as the whole assignment's called motion 4.
Okay, so thank you. Okay, so if it can be reduced to an equation, or if there's one new equation to distill out of all of this from motion 4, it's this one. You guys are telling me, right? Just make, okay, cool. And you're telling me, and Kat is telling me, and you're telling me that this thing is new. Oh yeah. First of all, we haven't had a motion or equation or anything prior to this in the class, or certainly with Walters. You didn't have anything before that had a cosine in it, and you didn't have anything that had an omega, that lowercase Greek letter in it, right? This is the introduction of cosine and introduction of omega at the same. Yes, okay, that's helpful. And yes, okay. Oops, sorry. All right. Okay. Let me back. So this cosine thing, you're gonna stop me, or when, so let me make sure one last thing. Then maybe I misspoke. So what you were trying to verify or play around with in the lab or the simulation or the whatever, the investigation, you were trying to test whether various systems did or did not fit this equation, whether various systems, like in other words, you were trying to find out whether something's a harmonic oscillator or not by saying if it fits this equation, that it is a harmonic oscillator, and if this equation doesn't adequately describe it, then it's not a harmonic oscillator. Is that a fair thing? By graphing it, okay, by graphing X as a function. So, this is very good. That's a really good answer, Michaela. So you're saying that what you did in lab, the kind of graphs that you were looking at to see whether they were like cosine or not, you were looking at, presumably, again, I'm not trying to trap anybody. I'm trying to make sure. So this is like a yes or no question. But when you say you were looking at graphs, presumably on your graphs, you have time measured in seconds on the x-axis, on the horizontal axis, and you have like position measured in meters or centimeters or something. And you're trying to see whether your graph, or you did try to see whether your graph like looked something like that. Is that fair? Wait. Oh, okay, wait. And oh yeah, Logger Bro is very stressful. Yeah. Okay, wait. This is good. And again, we are here to discuss, guys, like whether, you know, we call it lecture, but no, you can say your feelings. Like we are here. Like I used to hate labs so much. I can't even tell you, like as a student, I was horrible in lab. I couldn't stand it. It never meant anything to me. I didn't even know, every lab was just a constant reminder that somehow physics was a science. And I didn't even think of it as a science. I thought it was like a math plus philosophy or something. Like, but lab's super important, right? So we're here to try to make sense out of labs. So everything you're telling me is very good. And if Logger Pro is driving you crazy, you're not alone. Let's talk about that. But hold on, wait, so I'm trying to catch up in the chat now. But it is important for me to try to visualize what you were trying to do so that, you know, and we keep changing and adapting to quarantine and stuff. So when you say you were, okay, correct. You're saying correct, finding the best fit line. Okay. I'm just looking. It was a position. Okay, that's important. Like Rahel's answer, like when you say graph, the first thing I have to know as a physicist is what are their axes, like graphing. And if you're agreeing with me that your graph you were looking at something that somehow was position versus time, then we're on the same page. And yeah, if you're making a position versus time graph, then hopefully your data falls in this cosine thing. I'm just right, but if not, then not. Is that, and yes, Logger Pro is very difficult. Hold on a second, but yes, okay. So I sort of, that's one way to explain. Okay. All right. So good. If that's what you were doing. Okay. Wait. Let me know. Okay. Oh yeah. Okay. No, that does make sense what Veronica wrote. And yes, and Logger Pro is difficult. Okay. I'll try to help with this. And especially, oh my God, Logger Pro is difficult in the lab at John Jay. It's difficult. And we can usually explain it once we're like sitting there with it with someone who's struggling with it. But yeah, it's difficult and annoying. But my God, you at home doing this on a simulation, I don't even know what that experience is like. I can't even imagine how difficult that is. I don't think I would have the patience for it. But one thing that's important to know about Logger Pro is, okay, all Logger Pro is meant to be, it's important to remember, Logger Pro is just a way of getting data into the computer. Like that, I mean, so that we can turn our random measurements into graphs and stuff like that. But basically Logger Pro is just one big fancy table of values. But it really can get in the way, yes. But this cosine thing, okay, if I'm understanding correctly that you were throwing your data on position versus time axes, like every unit of time, you're measuring where some object is, and the object is where it's some kind of oscillator, but we're trying to figure out whether it's a harmonic oscillator. So you're tracking where the thing is as a function of time. You're throwing that information into a scatter plot, like into a graph, where the axes are just that: time, the independent axes, and position, the dependent axis. And what we're positing, what we're all, or Walters is positing or conjecturing, is that if this data falls into what looks like a cosine graph, then it probably is describing harmonic oscillation, and if not, then not. Now, so like where did that come from, or why are we all of a sudden talking about cosines? Well, first of all, so this x equals a cosine omega t thing, it's what, if it's true, and it is true, that means we're saying it is an example, a working, usable example of an equation of motion for an oscillator. Now I want to pause on that for a second, because like that means something. Like all of physics is about motion, and all of physics ultimately is equations, right? So in some sense, like every equation in physics is like an equation of motion, but some are particularly called equations of motion. In fact, our job ultimately all the time in physics is to We do a lot of equations about a lot of things. But what we're trying all the time to get for any given behavior or any given setup or any given system, we're trying to find an equation of motion, specifically meaning we're always trying to get a situation where time is the independent variable and position is the dependent variable. We're always trying to get, like your axes are set up that way. But we don't always have that. But we're always looking for some rule or pattern for a given setup that says if you name the time that you're interested in, the moment in time you're interested in, I could tell you where the system's going to be at that moment. That anytime we have x as a function of t, we call that an equation of motion. The original version of that from physics 1, like the original version that everybody's familiar with, and it's always important to bring things back to this, hold on. What you're all familiar with I think, I hope, I whatever. And, there's different subtly different ways of writing this. You can include an x naught or whatever, but x equals 1f at squared plus v naught t, that early equation from early physics. That is an example of an equation of motion. Like, it comes up a lot because it's doing just that. It's saying, like, if you name the time, we'll name the place. But that equation of motion assumes a certain condition, which is constant acceleration, right? Frequently free fall. Our job as physicists in general is, no matter what the situation, whether it's constant acceleration or what, we want to be able to come up with an appropriate equation of motion for the situation. Here, our situation is oscillation. We don't have constant acceleration. We have constant wiggle back and forth. We're trying to see if we have any kind of equation of motion that can describe that. And what you are conjecturing, or what Walters was conjecturing, whatever, is, cosine, like if we have enough math in our background to recognize the cosine function of math, it seems like that has the right quality here to describe an oscillator, because cosine goes back and forth, and so does an oscillator, right? That's just a conjecture. Like, it doesn't prove anything at all, but it's just like cosine, in fact, is the simplest mathematical function any of us can think of that at all begins to go back and forth. Like, we're guessing it not to make things more complicated, but we're guessing it because it's the simplest thing we know that might possibly smoothly work. And I'm going to pause this. So we're guessing cosine. Okay, we're basically saying, yeah, I totally believe it. Yeah. Okay. I'm just looking in the chat for a second. I may or may not be able to address this right yet, but well, that's nice. Wow. I'm looking at the screenshot in the chat. I made sure. That's very nice. That's impressive. Okay, and by the way, and that screenshot, or I'm just opening up. Sorry, I didn't share it, but it is shared in the chat. I think you can all open it. That's awesome. Right, I think. Yeah. screenshot does express like, yeah, after all the pains in the butt with Logopro and everything, if you just watch something go back and forth in a lab or in a simulated lab, like, and you just throw the data onto a position time set of axes, the shape you get is most closely reminiscent of the cosine shape in math, the back and forth shape. And I'm saying cosine, by the way, we could also say sine, right? Sine also does that, but sine starts at 0, as you may have talked about in the lab. And the physical oscillators that we're talking about, like if 0 means the equilibrium position, then when you place an object at equilibrium, you don't expect it to go anywhere. It'll stay there forever. We deliberately are starting our oscillator at some amplitude position, at some displacement from 0. And that's more appropriately modeled by the cosine graph, like which starts at, which has a y-intercept of not 0, if that makes any sense. Okay, so we are conjecturing, like you get that data and then you say, okay, I think a cosine model would work here. Okay, but it doesn't prove that it does, but it just seems like a good idea. And if it can work, it works. Again, to satisfy what goal? The goal is to be able to predict where this thing is as a function of time. Okay, so you predict cosine. That's what this English here is saying. But so what? Where did the omega come from and the A and everything, right? Like, well, from here. Wait, I better save if I haven't saved it. Okay, so this is a rhetorical question I'm putting here. I'm not actually asking you. I might have just lost you. Hold on, sorry. Hello. Hello. Oh, okay, sorry. Yeah, I like that graph from Logger. No, that was cool. Sorry. I'm asking a rhetorical question here. So I'm saying, like, what I'm trying to argue, okay, if look, our job is to predict where something's going to be when. That's always our job as physicists. Right now, our context as physicists is oscillators because they're like really fundamental ingredients of like the whole universe, basically. I mean, in short, I mean, there's many other reasons as well. But right now we used to look at things that like dropped or move with a constant acceleration. Now we're looking at things that have a constant wiggle back and forth, right? So we're trying to come up with a mathematical equation or expression that will make our prediction for us. So now we're guessing cosine because the lab data seems to fall into like a cosine pattern, right? So we're guessing cosine, but why don't I just simply, if I'm trying to keep things simple, which I am, we're not trying to introduce anything just to make things hard or complicated. I would want it to say the simplest thing I could, which is, okay, maybe x equals cosine of t. Like maybe that's my equation of motion. I'm trying to, I want the simplest way to make predictions about this oscillator. So I might just guess x equals cosine of t, right? I should, but I can't. That's too simple. I'm telling you, like, this is not a question to you. It's a question to think about. X equals cosine of t might almost look like it might work mathematically, like mean something. But scientifically, this cannot be the rule that we're looking for to describe an object moving through space as a function of time. It can't be because as a scientist, I notice that the units are wrong. And this is really what separates science from math. Like, I mean, everything in science, all the math that we do, and I believe in and love, all the math that I love, all the equations, I'm only allowed to imagine that letters stand for numbers if numbers stand for measurable numbers, like everything is a measurement if I'm a scientist, and everything therefore carries a units consideration, right? For real, for real. So I actually, as a scientist, cannot take the cosine of a minute or a second. Like literally, that doesn't make any sense. You take the cosine of angles, right? And Lord knows why angles are going to come into this discussion, or maybe you do know, but and maybe I said this last time and stop me if I did, but like what I'm trying to say right now is like we're always looking for the simplest possible model that could be right. We really are. As much as it doesn't look that way in science, science is always trying to find the simplest possible model to describe reality. Reality is already complex and a mess. We're trying to make sense out of reality. So no matter how messy or complicated science always looks, that's because like the reality is messy. We're always trying to find the simplest model we can, but the simplest model we can, the simplest model that actually works, right? So I start with this cosine idea here, but just cosine of time, too simple, doesn't work because literally the units don't work. You can only take the cosine of angles, which are measured in angle units like radians or degrees, which we're going to have to talk about in a second. You cannot take the cosine of a second. So, sorry. Okay. All right. First of all, we have to get into something here, unless I already did last week, but I don't think I did. Cosine is coming up because wiggle, wiggle. Like cosine is coming up because of whatever anybody might ever remember about the cosine graph, which is wiggle, 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 right? But the first thing we all know about cosines, and by the way, I'm assuming way in the back of my mind that you don't, we're going to talk a lot about cosines here and all that stuff. Nobody here is assuming that you guys come into this room loving cosines. Okay, I'm just to be clear, like I love cosines. Walter loves cosines. Like we love our trig now. We didn't used to, number one. Number two, one of the things we love about this class is it turns out like one of the secret background agendas of this class is to get everybody to actually be okay with trigonometry and to love it by the end. But that means we don't actually assume that you, like every time we say cosine, that your heart bleeds for joy right now. Like you might be dreading where this is going. But cosines and all that are actually easier and cooler than they might seem. Okay, so for the moment, I'm going to say this. You take the cosine of angles, right? Whatever it is going on when you take a cosine, and we're going to get to that, but whatever's going on when you take a cosine, it's something you do to angles. You input an angle, you get out a cosine. Now, angles, when you're in like 7th grade or 10th grade or 12th grade, can be measured in degrees. The truth is the better way to measure them is radians. We're going to talk about all that, but I don't care for the moment. If you want to stay in degrees, you can. Just understand that whenever we're going to deal with a cosine, it's going to have to be applied to an angle. And every time we say angle, I'm going to say radians. And all of that means that all of this means for the moment, and I'll get back to the Neanderthal thing in a second but anyway, but all of this means that if that's all true, again, well, if that's all true, then unit wise, if we want our input to have anything to do with time, and then we want to take a cosine of that and spit out an output that has anything to do with distance, what I'm arguing right now is there's got to be some constant. There's got to be something right before the t to make the units work out. I mean, I know you already know what it is, but I'm trying to justify why it's there. Sorry, excuse me. So I'm just writing some constant here. There's got to be, and more specifically, what I mean is, whenever I put square, my handwriting is bordering on axe murderish here. I'm sorry. Whenever I put brackets around, like square brackets around something, what I tend to generally mean when I do that is the units of, like that's my let's analyze units symbol, the square brackets. So I'm saying we're trying to build a function here. Like we're trying to build a function. Like believe for a long time in science, I thought the point in science was that people gave me formulas or equations or functions, and I would plug things into them and use those equations or functions to get results. It turns out what you're really doing in science is you're trying to come up with those equations or functions in the first place. That's what we're doing here. Again, I already know you already tested it in lab with Walters. Like I'm not trying to lie to you or trick you. Like the answer like that you were tested is right. But now I'm trying to show you where that answer came from in the first place, or how we even built it, why we even thought to test it in our minds. Well, the cosine we conjectured because of wiggle, wiggle, wiggle. But now I'm saying if there's going to be any accuracy at all to this idea of you plug in time, I take a cosine and get back a space, then we're going to have to plug that time. I mean, I'm sorry, we're going to have to multiply that time that you input, that independent variable. We're going to have to multiply it by some constant that I don't know anything about yet, but I know it's constant, whatever it is, some number, and it's got to be a number measured in radians per second, so that literally the seconds of t cancel out with the denominator of whatever this constant is, and we're left with something in radians, and then we can take the cosine of it. Like I'm literally arguing by just by virtue of units, or what you call dimensional analysis or stoichiometry, just by that alone, if a cosine function is going to be our equation of motion, there's got to be a constant before the t. So I'm going to now, if that's true, and I will pause. Oh, no, I will pause. I'll look in the chat for a second. Hold on. Oh, yeah, right. Wait, what did I say? Yeah, radians. So I agree. Sorry. Yeah. So totes migotes on what Kat's saying in the chat. Like, and sorry if I missed it when it was relevant, like how many minutes ago? Like 2 minutes ago. Right, this thing that I'm talking about here is what we ultimately call omega, or angular frequency. In fact, let me go there right now, right? I'm saying there's got to be a constant there. All I know is it's got to be there, and it's got to have certain units. Now I'm going to give it a name. I'm just going to give it a name to hold its place there, right? Like you could call it X, except X is already a variable. I'm not calling that. I could call it C for constant, but that's already used for something. So I'm just going to call it a Greek letter because we're running out of English, right? We're gonna call it lowercase omega, and it's going to go there. It's going to be that constant, which again, all I know about it right now, like I'm not disagreeing with Kat, I'm totally agreeing, but I'm saying right at this moment, all I know about this omega thing, and please again understand omega, which I just wrote inconsistently, is just a letter that we chose. Like, I mean, there's reasons for it, but we could have chose anything. So that, but all we know about it right now is that whatever this thing is, it must measure something in radians per second. Okay. I want to analyze the bejeebers out of that. Like, and yes, we're going to call it angular frequency. Yeah, we're going to analyze that so much that before we do, let me just finish the rest of this expression. Like, so far we have Like so far what we're saying then is we first conjectured that x had to be some kind of cosine function. So some function of a cosine thing, right? Like it could be more complicated. We didn't know it could have constants. So it was just some kind of function of cosine. Now we've established there's got to be some kind of letter, some kind of constant before the t. We're calling that letter omega. Okay, but we're not. So now we're saying it's got to be some sort of function of x. Has got to be some sort of cosine of omega t function. But I don't think we're done yet. We're almost done with our conjecture, and we will test, and you test it in the lab, but I'm almost done like trying to make sense out of why this conjecture came up is great. If you plug in radians per second multiplied by seconds, you'll get radians. So then you'll take the cosine of a radian of some number of radians and you'll get something, but what you'll get is a number. Like the cosine of pi over 2 radians, for example, is like the cosine of pi over 2 radians is 0, for example, or the cosine of 0 radians is 1, or if you like degrees better, like the cosine of 60 degrees is 1/2. Where I'm going with this though is the cosine of 60 degrees is not 1/2 degrees, nor is it 1/2 meters. And this is important. Like, even though we just fixed ourselves so that what we're inputting into this function are proper radians, and that's a good thing. You cannot take the cosine of anything but a radian or degree. But then what cosine spits out is a dimensionless number, like for sure, like by definition, like the cosine of 0 is not 1 meter. Or I'm not yelling at anybody, I'm just like yelling because I'm excited. But the cosine of 0 degrees is not 1 meter or 1 degree or 1 radian. It's just the number 1, right? Because ultimately it's like meant to be an x coordinate on a unit circle or something. So as it stands now, if we take the cosine, we just spit out a number. But what we're looking for something to be spat out that has units of meters. We want a displacement, a position, an x to be spat out. And furthermore, we want our x to be able to range between two endpoint values like 15 centimeters and negative 15 centimeters or 50 centimeters. If it like x is supposed to range back and forth between some high amplitude and some negative amplitude position. The cosine graph does that, but specifically it only does that between -1 and 1. Like if I just allow cosine to spit out values, I'm never going to get anything greater than 1 or less than -1. And like that would imply that the farthest my mass could ever extend past the spring equilibrium position is 1 meter or -1 meters. What if I want it to be 15 meters? Or what if I want it to be 15 centimeters? In other words, I'm going to add one more thing. Right? And sorry. So what I'm saying here now is before I even test, or if again, I'm sort of going back in time, like to the headspace I might have had when I first made up this cosine function, when a physicist first made up or tried the cosine function that you were trying in the lab, where their brain would even come up with this is they start with the cosine idea, just like you saw in Logger Pro. Then they adjust it with the omega because we've got to adjust for radians. And then they adjust it one more time before they even try anything. They multiply the whole thing by what we're calling A, or you could just as easily call X naught. And what do we know about A or X naught or whatever? Well, first of all, that's supposed to be some kind of position measured in meters, right? Because cosine is going to spit out just numbers like -1 or -1/2 or positive radical 3/2 or +1. It's just going to spit out numbers. But then A will be some kind of number that is that is measured in meters. A will be some kind of initial or some kind of position measured in meters, so that we'll multiply a dimensionless number by a meters number and get a full answer in meters, as we should. Furthermore, and you could already see this, like as long as by A, whatever that number is, A is the number of meters that we measured when t equals 0, as long as that letter A is the initial value of X, then this works perfectly if you think about it, because this value right here, A, that we're going to put, that you call the amplitude, like whenever t equals 0, because the cosine of 0 is 1, right? That's why we chose cosine as opposed to sine, where sine of 0 is 0, but the cosine of 0 is 1. We like that cosine starts somewhere on the y-axis. Well, wherever it starts, we want to multiply that, scale it up. We don't want to have to call it 1 nothingness. We want to be able to call it like 0.15 meters. So we just literally multiply that by 0.15 meters or whatever A is. In other words, when t equals 0, the cosine of 0 is 1. So this whole thing will be 1. And therefore X, when t equals 0, is whatever that value of A is. Like that should work. I'm saying this is all I'm trying to build a function that makes sense. So I'm saying I start with the shape called cosine and I add constants to adjust for units until this at least seems to make sense in the limiting cases, in the extreme values that I know in advance. Like I know what should be happening at t equals 0. So I test for that. Right? So this is now my work. This was your working conjecture. A equals a cosine omega t. I have a lot more to say about omega, but this is the basic reasoning behind it, behind this function. So I want to go on and say a lot more about omega, but I'm going to pause for 1 second. First of all, I'm going to turn on the lights. But second of all, just let that sink, like, I don't know if that's clear or not. So tell me if anything I'm saying is either not consistent with what you said with Walters, or if it's confusing or something, just. I mean, I guess that's my question for the moment. I have more to say. I want to analyze omega and do stuff with it, but like, is everything I just said, is there anything that's inconsistent with what you did with Walters, or anything that doesn't add up, or where is it okay? I'm gonna not so far. Okay, cool. That's it. Thank you. I appreciate it. I'll take it. Thank you. Okay, that works for me. Okay, that's over. Here comes speaking of which, speaking of Walters and contradiction, you realize that while all this goes on, he and I play chess, right? Like he always is winning. And so we take turns. I mean, all through life, we're always taking turns over. So I don't know who's. So when I think of him, we'll make the next. Maybe we'll make the whole next move against him as a group. Checkmate that bastard. All right. So. Oh yeah. All right. So I got to talk about radians now. Right. Okay. Omega. Now, again, clearly you already know stuff. I mean, at least one person cat has put in another. I know that you already know something about omega, like from the lab. You know it's called angular frequency. I'm not trying to take that knowledge out of you, but again, I'm just trying to sort of build it up. But I'm not assuming that just because you know it's called that instantly makes sense or anything. So let me try to make sense out of it. As far as I'm concerned, right at this moment, all I know about omega is I stuck it in there because units demanded that I do that. That omega is something that's measured in radians per second. Okay, well, anything's per second refers to some kind of rate. Like meters per second is a rate that we call velocity, right? And we're all familiar with velocity. This is like a velocity. This is some kind of rate, like how quickly we're doing something in time. Only it's not meters. This is not, whatever this omega is, it's not measuring how much space we traverse per unit time. This is measuring how much angular space we traverse in like a unit time. Like, yes, this is called angular frequency because radians are a unit of measurement for angles. So this has something to do with how frequently we're carving out angles. Yes, So I'm going to write that. Yeah, radians measure angles, and radians and angles are the only thing that you can take a cosine of. So radians angles seem to be coming up here, but now we're saying that this rate, this angular frequency, is how rapidly or quickly some kind of angles are being covered. And that is a weird thing to say because we're looking at a system that's going like this, like a mass on a spring going straight back and forth. Like the oscillator we're looking at, I mean, it might also be a pendulum, but our original oscillator, the one that we spend the most time thinking about, is something that's just going back and forth in a straight line. And yet suddenly we're talking about its wiggle rate in a way that has to do with angles, and that tends to confuse people. You're lucky if that confuses you at all, that's good, because that means you're thinking directly at it. And there is something about this that at first does not make sense. If you're never confused about this all, it means you're not looking really honestly at it. I mean, so let me say again, the thing that might be a little confusing at first is we are talking about a harmonic oscillator in its purest form. We're talking about a system that's going like this, straight back and forth, straight back and forth, straight back, right? And again, it could be a pendulum that's going like that, but it definitely doesn't have to be. We're talking about something going back and forth, and yet we're measuring something about how many angles it carves out per time. So a very fair question is, where the heck are the angles? What does angle have to do with something going straight back and forth? I'm not asking you guys, I'm just pointing out that that would be a reasonable thing to wonder here, a very reasonable thing. Like, and again, you might even answer it by saying, well, I guess the angles are coming up because cosines are coming up, and the cosine's coming up because this thing's wiggling. That's a half answer, but it still doesn't, I'm still have a right to be confused, especially if now I'm saying we're going to measure our angles in radians, and many of us, just because radians have come up in a math class before, that doesn't mean we're all very comfortable or like radians. So I'm here to talk about radians for a bit and show you why they have to do with this. Okay, so the question I want to try to answer now is, if we're going to look at something oscillating in a line, I wrote oscillating back and forth, that's redundant, but if we're picturing a mass on a spring oscillating, going back and forth within an axis, within like an x-axis, within one dimension, then like my question that I'm not asking you guys, my question that I need to answer for us, I mean, unless you want to, is what is the meaning of radians in a discussion of something going back and forth in a line? Like if we say it's oscillating at a rate of 40 radians per second, what does that say? And again, I'm not asking, I'm just posing the rhetorical question. How do you measure something going back and forth in a straight line in radians per second? Okay, and maybe there is an answer in the chat. You are welcome to answer. I'm just not saying, I'm saying you don't have to, boy. Let me look in the chat. Yes, that's awesome. That's beautiful. And that's perfect. And also, by the way, okay. And by the way, and if I did say this last time, then please stop me and we won't do the whole same lecture again. I just, I don't, maybe I did. Wait, did we do the omega equals 2 pi f and f equals 1 over t? Did we do all that business last time? I didn't. Okay.
Yeah, we talked about it in lab.
Oh, okay, great. Okay, cool. And I appreciate your honesty. And because and not to, because what Kat said here, don't radians have something to do with the motion is cyclical? Absolutely, that's the answer. That's hugely the correct and right and helpful answer. And I'm not trying to imply that she could only have known that if we had said it before or something, but I just want to make sure I'm not. So, but that is right. So where I'm going with this is, it is a radian. Well, yes. And the more you can, I mean, it's honestly, some years, I think this is the main thing to get out of this class is to actually learn what a radian is, because it opens up so much later in math and science to actually not be intimidated by radians or to not be held back by them. And most people are. So this is that part where we kind of learn that here. And maybe you already did in the lab, but like, so what I'm saying is this, okay. It's true that radians are to angles as like inches are to distances or whatever, right? Radians are just like the subdivision, the unit that we divide angles up into, and to say that one angle is bigger than another is to say that it has more radians than the other. Okay, but that doesn't tell you anything. I'm just, yes, radians are the way we measure angles. But the real question, though, is what is an angle? And this is important to pause on for a second, because especially if we're going to say that looking at something going back and forth, that all of a sudden we have to worry about angles measured in radians, like it really does raise the question, why the heck are angles coming up? It's something that's going straight back and forth. And the important thing to realize about an angle, and this is the thing that gets lost by everybody with all the trigonometry and everything that people do for years, it's all based on angles. And what people think, people tend to think of angles as intersections between two lines. Like when people think angle, they tend to think like V. And if someone says that's a really big angle, they tend to think that like this is a big angle, it's bigger than that one. That people tend to think, oh yeah, you're saying that's like a more spread out V than some other V. And when I say people, I mean me. Okay, like practically for most of my life, even doing physics right. I mean, even before I met Walter, it's like if someone said angle, I'd think V. Okay, but that's okay. But that kind of like distracts you from the whole thing of what an angle really is. If you think of it as the space in a V. If I think that this angle is smaller than this angle because the two legs of this V are closer together than these, I've kind of confused myself if I think that. And I think that's intuitively, I mean, unconsciously what people tend to think, that a smaller angle means a thinner V. Okay, I'm not saying it's wrong, but that's a misleading thing to think, because like an angle is not the spread outness of a V. Because, okay, first of all, if an angle, if I'm saying this is a big angle because this is like a sort of big V, if by that I mean this hand is kind of like far away from this hand. Well, first of all, are you just dropping a straight line from my top? Like, are you just measuring like that this hand is like 3 inches from that hand, like over here, like along a straight line path? Because if that's what you're saying, like this V is bigger or smaller than, and please, I know this is a very weird point that I'm making, but I'm saying angles, don't think of a small angle as a thin V and a big angle as a wide V. I mean, you can think that, but realize when you think it, there's something really weird about that thinking, because this V, if I'm saying it's thinner than that V, I'm saying these spokes, my hands are like closer together here, but close means distance. It means like if I dropped a line from some point on my hand to the other hand, then that line would be a shorter line than like the one that I would do over here. But that can't be what we mean by angle, because we already have that. That's just called distance. That's just saying this hand is farther away than that. That's not what we mean by angle, right? Also, that's not what we mean by angle, because where are you going to drop that line? If you drop it out here, then you get a really big line. But if you drop it here, right? So what we mean by angle is that, first of all, you got to drop a curve. What you're really talking about when you say that this angle is bigger than that. You mean if I open up my hands like on a hinge, like if my fingers spread out from the other fingers along the arc of a curve, you're saying that the arc length between my two fingers, my two hands here, is a longer arc length than it is if I put my hands there, right? First of all, you're talking about an arc length when you talk about angle. Second of all, you got to, wherever you're going to measure between my two hands, you got to measure at the same place for both of them for it to be fair, right? Like obviously these two hands are really far apart if you measure way out here, but they're really close if you measure here. So wherever you're going to measure, you got to agree to measure in the same place. Well, all of that is a very complicated way of like trying to force the V into a whole ratio thing, a much simpler thing to say than all of that. Once you realize you're involving arcs of curves and all this, then what you realize is, no, what an angle, okay, so all of that is like the wrong way to think about it. To really think about an angle, what an angle really is just a portion of a circle, right? When we say that this V is wider than this V, we're really saying I opened up more of a circle with this V. And this is really an important point again. It may, hopefully it sounds so obvious that it sounds boring while I'm saying it. But if ever in your life you think of angles as V's, don't. Think of an angle as a portion, a section, literally a fraction, in fact, literally a fraction, like a numerator denominator, of a circle. Like everybody in the world knows what this angle is. Like everybody in the world, you can call it 90 degrees if you want, or I'm going to call it pi over 2 radians. But I'll tell you that what we both know, I mean, the Greeks didn't call it either one. The Greeks did not, and they did all this math that we're using today, right? It all come from the Greeks, and they didn't call this a 90-degree angle or a pi over 2 radian angle. They just called it a right angle. And we all know what a right angle is. And what is it? We can recognize it no matter how big my hands are. Like whether we measure way out here or we measure here, what we're saying when we see a right angle is we're recognizing quarter of a circle, right? Super important. Right angle is quarter of a circle. That's what it is. And when I say that, I'm even saying something important about circles when I say that. I'm tacitly assuming that all circles, regardless of their size, carve up the same way. Like this is a quarter of a circle, whether I'm thinking of this circle here or that circle. My hands right now, when they form that like that L thing, that's a quarter of a circle. You know, this is a 180, whether you, this is a half circle, whether you call it a 180 or a pi radians, or when someone's snowboarding or skateboarding and they do a 360, right? And everybody knows what the 360 is. Now, the truth is why we divide that thing into 360 is a whole insane thing unto itself. Everybody thinks they're used to 360s and they get degrees just because they're used to it, because they know 360 means full circle. 180 means half circle. Then you convert, then in math, when you have to do radians, then we say 2 pi radians, pi radians. It doesn't matter what you call it. What we're all recognizing is that an angle is a portion of a circle. And in fact, specifically, what it really is it's a portion of the circle. Like meaning if you're looking at a pizza, it's a portion of the pizza crust, like the actual circle, right? As long as we all agree in advance to all cut our arcs from the same circle. Like in other words, a 180-degree angle is twice as big as a 90-degree angle. It's a 180-degree angle is twice as much arc length as a 90-degree angle, as long as they're both cut out of the same circle. So that's why ultimately what an angle is by definition, is just arc length divided by radius, right? We're just saying it's arc length, really. But just if you happen to cut your arc length from a pizza that's twice as big as mine, if you happen to cut your arc length from a circle whose radius is twice as big as mine, well then no, you didn't cut out twice as big an angle. You just cheated by having twice as big as a circle. So you got to divide your arc length by 2, and because your radius was twice as big as mine, and now we'll end up with the same angle. Like that's all. Angle is just the pure ratio, the ratio of arc length to radius, which really just means it's portion of circle. I'm going to say this one last time. Like when we say that this is the definition of an angle is arc length divided by radius, what we really mean then is angle sorry. Okay. Yeah, the chat, sorry. And maybe Walter said all this. God bless him if he did. Hold on, sorry, man. Oh, we didn't put yes. Okay. I think I agree. I think I've lost what the area between A and B, but yes, but I didn't. Okay, so this is important. If I didn't say this, just is, so what I'm trying to say right now is that an angle really is, it's literally a fraction. It's like a pure fraction. It's like a pure ratio of one number to another. It's like 1/4 or 2/3. A radian is not actually a thing. Like it's not actually a unit like meter or kilogram or second. It's actually meters divided by meters. It's a pure ratio, and then it's the most direct way of measuring that ratio that represents what portion of a circle we're talking about. So the most direct example Okay, so just to see, and again, I know all of this is old news in a way, but I'm just trying to put it in a perspective that hopefully is helpful for physics or clarifying. Now I'm saying, I'm trying to really explain what radians are and then how we measure angular frequency in radians per second in physics. I mean, for whatever that's worth. And I think this is useful even if you feel like you know what radians are. I think this can still be useful. But so remembering that what an angle is just a pure ratio. It's just a fraction of a circle. Like a right angle in my mind is 1/4 of a circle, right? Now you can call that 90 degrees if you want to divide the whole circle into 360 parts. Nowhere in here have we said to do that. I mean, and again, if you say that the whole going around the whole circle is 360 degrees, it's because you've decided to say that it's somehow worthwhile or meaningful to divide one circle into 360 subdivisions. I mean, which I'm not saying you can't do, but we have no reason to do it yet. But let's just see what we get if we do, like, what if we want to measure the angle that brings us around a full circle? Well, if we go a full circle, then our arc length, the amount of crust we would get of this pizza, the full thing would be the full circumference of a circle. And the circumference of any circle is 2 pi times its radius, right? All circles bear the same ratio of circumference to diameter. So if I go around a circle, regardless of what size it is, any circle, if I go around the whole thing, the circumference is 2 pi r. Therefore, right. Well, yeah, okay. I'm gonna leave the list like that. Okay. I want to bring this back now to something Kat said before and then say more about it. But this is a lot of verbiage, but to try to nail down, like in the end, what I'm saying is an angle is a portion of a circle. Like a bigger angle means a bigger portion of a circle. And by portion, I literally mean fraction. So a right angle is like a fourth of a circle, whatever numbers you put to it. How to get exact numbers to compare one angle to another, the most direct way is to take the direct definition of an angle. If an angle is a ratio of arc length to radius, which just really means that an angle is just size of arc length, but assuming a radius of a certain size, like that's all it really means, right? So if bigger angles means you've carved out more of your trip around a circle, then since the circumference of any and every circle in the world is 2 pi r, 2 pi times its radius, that means that to go around a full circle from now on, we're always going to call 2 pi radians. Like a radian is just that ratio of arc length to radius. So from now on in my life, whenever I think of a circle going around the whole thing, I'm going to think just the same way that I think, oh, look at that 360, like with skateboarders or whatever. If someone does a full circle and I think that's a 360, what I'm saying right here now is, well, even better, it's a 2 pi radian. If you think it's a 360-degree turn, then it's a 2 pi radian turn. Furthermore, if you do a half circle from now on, I'm calling that pi radians. If you do a quarter circle, I'm calling that pi over 2 radians, okay? But then why I'm saying all this is because what we're looking at, we're not looking at any geometric circle. We don't have, we have a mass that's going back and forth within the straight line on a spring. There's no circle to be seen. But what there is, and again, this is Kat's point, I'm just saying because it was, what we're seeing is not circles, but we're seeing cycles. We're seeing something where everything is changing about an oscillator. That's the thing. Every single moment in an oscillator, position is changing, velocity is changing, acceleration is changing, force is changing, kinetic energy is changing, potential energy, like every moment in an oscillator, every point in time, every point in space, the value of any conceivable measurement is changing, right? That's what, in a way, is fascinating about an oscillator. That's literally true. And that's not a throwaway statement. Like, that's not true in free fall. In free fall, your position is changing, your velocity is changing, therefore you have acceleration, but we say your acceleration is leveled out. In an oscillator, everything is changing, yet what's not changing is that fact that everything is cycling, that there's a rhythm to it, right? And each cycle now we're going to analyze with the mathematics of circles. Each cycle of back and forth, of there and back, each round trip, each repeated pattern of behavior, of motion, each cycle, we're going to say consists of 2 pi radians. Okay, that's like the connection here. That's what we're saying, that if we believe that for no matter what size circle in the world, that there's always 2 pi radians in a circle, then we're going to say, yeah, no matter what size cycle in the world. In fact, no matter what kind of cycle, whether you're cycling through linear positions, or you're cycling through angular positions, or you're cycling through temperatures, like homework 2, or you're cycling through electric field magnitudes, upcoming homework, whatever you're cycling through, if you're cycling through some quantity, we're going to say that each one of your cycles, like big or small, whatever, we might not even, it's like, could be washing machine cycles. So I don't even know what it would mean for be big or small, but each one will have the size of 2 pi radians. Okay, that's our first connection. So So when we talk about angular frequency from here on in, if someone says that an oscillator, and this is the joke, the Walters point, presumably, I hope, if someone's saying this oscillator is oscillating at an angular frequency of, actually, let me write this one down. Sorry. And I will take a breath. Whoa, sorry. Okay. In a minute, I really will. I keep saying I'm going to take a breath. I really will. I want to do this one more example with this, provide one more example for you guys, and then I'm going to shut up and like let you do something or have you do something. But let me just see if this is clear right now. So what I'm saying. So I'm trying to, in my way, and again, hopefully this is just another perspective on the same stuff, Walter, you were doing with Walters. But I'm trying to say the reason that we're going to be describing oscillators, the reason that the equation of motion that you tested and verified for harmonic oscillators, like has a cosine in it and has this omega thing in it. The omega is a measurement of angular frequency. Sure, the omega, as you might know, is like how many humps there are to your cosine graph per unit time. But like, what does that mean in English or whatever? Well, if omega is measuring radians per second, as long as we always understand, as long as we literally think of it as a conversion factor, you can, I mean, I should write it down as a conversion factor, like one cycle equals 2 pi radians, that is what we're saying, or there's 2 pi radians per every cycle. Then if we have an oscillator that's described as x equals a cosine 2 pi t, if omega is 2 pi, that means the thing is doing 2 pi radians every second. That literally means it's making one cycle every second, because there's 2 pi radians in a cycle. So it would literally mean that the thing is going like there back every second. That's what the omega means. Omega ultimately tells you how many cycles per second you're doing. There's a conversion factor of 2 pi is one way of saying. Does that make sense so far? I mean, or is that consistent? Is that okay? Is that okay? So, okay, I'm going to assume this. We're going to see if this is okay, because I'm going to give it to you in a second, but yeah, all right, I'm going to develop this one. Actually, yeah, I'm going to throw it to you. So what I'm saying, you'll see. um, okay, so notice this, we're about to go, so I'm now about to make a couple of conversions here, or like new equations, if you like. You'll tell me in a minute, like, well, you'll see if these are familiar or not, but I'm saying now, okay, x equals a cosine omega t is like our equation of motion for an oscillator. It's supposed to be a rule that allows you to plug in time, and then it will spit back out position for any oscillator, right? But it has this hidden, not hidden, it has this included constant omega in there that I'm not trying to unpack and explain. Omega is angular, or like Kat said, is angular frequency, which means number of radians traversed per second. Now I'm reminding us that there's 2 pi radians in every cycle. So whatever is spat out to be omega, so this math expression, or like a logger or something, will spit out something that has an omega in it. And omega is measured in radians per second. And radians are what I'm saying they are. But that doesn't mean that they're intuitive or obvious or comfortable. It just means that they do make sense when you think about them. So if you remember that there's 2 pi radians for every cycle, we can take that number omega. What this is saying is we can take that number omega, the number of radians per second, and we can divide it like by the conversion factor by say, well, there's 2 pi radians per every cycle, and the radians will cancel out, and we'll have 1 over seconds divided by 1 over cycles. And you know how you divide fractions, you multiply by their reciprocals. In other words, the denominators will flip up, right? And what we get here, if you divide, is just what we just did on this prior page. Like if I tell you that something's omega, its angular frequency is 2 pi radians per second, then in my mind I could say, oh yeah, 2 pi radians per second. Okay, there's 2 pi radians in every cycle. So I'm dividing by 2 pi, like 2 pi radians takes me a full cycle. Oh, okay. So 2 pi radians per second really means 1 cycle per second, right? And if it were 4 pi radians per second, it would be 2 cycles per second. It's just a conversion factor. We're just dividing by 2 pi. If you want to change this strange angular frequency number, this strange thing that seems to have to do with cosines and all, if you just divide it by 2 pi, then you get a regular everyday thing that we call standard frequency. Standard frequency, which is now not measured in radians, it's measured in cycles per second. Standard frequency is measured in something called cycles per second. In fact, I'm going to go one step further. One cycle. Now this is important. Like this is not applicable. You didn't learn about this last year in physics or last semester, because this doesn't apply to a ton of physics. It doesn't apply to something falling down or blasting off to the moon, or an arrow like shooting to the other side of a battlefield. Like those things do not oscillate. They're not cycling. So no concept of, so we don't deal with cycles or radians or anything with those kind of physics phenomena. But now we're dealing with something about which, like, the one thing we know is that it cycles, right? So from here on in, and a cycle could be of any size or any type, just it's a cycle. So from what, sorry, I just totally forgot what I was going to say. Oh yeah. So from here on in, the idea of a cycle per second is such an important idea for, like, such an important unit for anything that is cycling at all, that we give that a name and we call it 1 hertz, like Hertz. Literally, I shouldn't even put, like, let me be more clear. 1 hertz in science, by definition, is 100% 1 cycle. Please stop me if I said all this last time. I don't think I did, but I do get my classes confused. 1 hertz is 1 cycle per second. It's like the man's name, Hertz. A little unfortunate because it ends with a Z, so it sounds plural, but it's not automatically plural. But you've heard of this idea in such examples as Now, I really didn't say this last time about, please tell me if I said this thing last time about megahertz. I feel like I'm, but all right. Okay, let's just pause. Oh, I did. Did. All right, I think I did too. Yeah, okay, thank you for your honesty. Okay, I think I did too. And then if, I'll assume that I did then on that. But then what it means is, I'll go back to that page if you want, but I'm saying then that to convert from angular frequency, so then you know, or I'm just reminding you, to convert from angular frequency to frequency, we divide by 2 pi. And then to convert frequency to period, right, the thing that you actually can relate to and measure or count or observe in a lab, you flip frequency, right? So I did say this again. Stop. I think I did. I'll go slower on this, but I didn't say it last time. But I think I did. And so, right. So just to summarize what I think. Oh, good. All right. Thank you. No, I appreciate it. Okay. Good. Super important. It's not a problem to say it twice, but I'm not going to like over say it. But just the thing to know from last time, then just remember then what like the summary of this is that these three things for all time, each of these three, I don't know how you want to say this in your notes, but these three quantities, omega, lowercase f, and capital T, angular frequency, standard frequency, period. They are three independently sufficient ways to measure or characterize an oscillator, right? Like you could talk about its frequency, and then you automatically know its angular frequency and its period. Or you could say its period, then you automatically know its angular frequency and its standard frequency. If you know one, you know all three. We wouldn't need all three. We would only need one to describe an oscillator, except that one, the period, is the most accessible and reliable information that we get from the lab. And angular frequency omega is the most direct and reliable that we get straight out of the math. And F, standard frequency, like links the two, the experimental extreme to the mathematical extreme. Like, and that's why we have the three. But you can, as long as you know one, you can navigate the other two. But I guess I did say that already, so I'll pause there. In fact, I'm going to really pause for a second. I'm going to collect my head. So just look up. We still have things to do and stuff. But could everybody just like pause, just like look in the notes to see if there's any loose end or any question either about what I've said so far or how it relates to what Walters did. Or by the way, if you got work to like, I'm not saying I don't have more to say, but I'm going to take a breath for a second and I'm going to meditate here, meditate on this for a second. Maybe I'll just stop and meditate. What the, until my son gets back. But what I want you guys to do besides just like look and make sure it's okay, feel free at any moment. If you've got something due for Walters, I should always make this clearer than I do. If you got something due for Walters, it's not, you're allowed, and especially if you guys have been working on it or you're confused or something, you guys are totally, in 2 minutes after we just look at this, you're allowed to bring up any questions you might have about something that's due for him, and vice versa the other way. Like when we have a test coming up or whatever, you're certainly going to be able to ask him questions. So if there's any, but your lab reports and stuff tend to mount up more than like lecture homework. So I can also be more helpful in clarifying lab and stuff if there's actually a thing that you're struggling with that you need straightened out because of an assignment. It's not cheating to raise that in class. So I'm saying now, let's all just think for a second in notes, make sure that what I'm saying, like it's supposed to help you do your assignments for him. So if what I'm saying even connects at all to anything that's due for him, but doesn't connect enough for you to bridge a gap, this is a good time to bring those things up. This is an appropriate resource to use. So I'm going to, again, it's not like I don't have other things to say, but let's just see if any of that helps you at all with any understanding or creates more confusion of what you're doing with him. I mean, think of him as like the leader and me trying to clarify that. Okay, so I'm going to just pause for a second so we can all look at that. good. All right. I totally appreciate that. I'm going to hang out for, even, that's totally helpful. Look, what Gabriel just said. I'm going to start preparing my board for the next thing. Like we still have an hour. I'm happy to let's go early if we're not taking a break. And I have an auction. I'd rather even do that than take a break. We can do that. But I'm going to start preparing my board for like the next thing where I'm going with this. So I'm going to turn off my board so I can prepare it without distracting any of you. Really do take another minute to see if there's, again, just consider it. If there's something that's due for Walters and I can be of any help now, that is a totally great use of class time in all directions. It is. So take a moment to look, and I'm going to turn off my board, like I said, for a second. Sorry, nobody needs that. That's for sure. Hold on, sorry. Whoa, what? Oh, I thought I was the host. Okay. I guess, all right. So, oh, thanks for noticing that. That's very nice that you noticed that. I would like to address that before I get myself too distracted. And it was a little bit cheesy and a little bit self-serving that I put it in there. I mean, a little bit maybe not appropriate. So but I am glad you noticed, and I will talk about the quick, and it does remind me of something we have to get to here in this class. The quick answer to is it's for fun. It's totally optional. It is not at all required. It's for fun, a thing and it costs a little bit of money, but it's not about, I mean, I can pay, like if anybody is interested in it, I can give them the money. It's not about making money or whatever, but it's a short story, like a children's book thing that's meant to get at kind of what it means to be a particle. Which is something we have to get to in this class, like the difference between a particle and a wave, which is really what this class really is about. And that's where we're really going in this class. So I will talk more about that thing. I'm glad you noticed, but it's totally optional. It's just meant for fun or silliness or whatever, and definitely nothing that anybody has to spend money on or do anything with. But I will get back. Thank you for reminding me. That actually does have to do with this next board. Let me prepare. But thanks. Hold on. Oh, wait, so sorry, one quick question. If I already did that thing with omega F and T in this class, did we talk about sixths of cycles and like a pizza slice that looks like an equilateral triangle? Like the pizza slice that looks like an equilateral triangle. Did we talk about that? Does that sound from? Oh, okay. Okay, just making sure. Okay. Okay. All right. Then that's one thing I want to, okay. I didn't, okay, thank you. I believe you. I totally believe you. So then again, give me a second to write something out here and you look over your notes. Okay. So if there's no quite, everybody's cool with, all right, then I'm going to put this board back. I want, hold on. Okay, so I would like you to copy this down. I've got, it's important if I didn't say it before. I'll obviously explain in a second, but maybe just copy down. And then I'm going to just. Sorry, okay, let me explain. So first of all, I just put an assignment in everybody's, I put homework 3, technically due next Monday, into everybody's box. I just remembered to do that. I mean, what, that's tangentially, that's related to the question about the short story that I put in. The homework starts to get at what the difference is between a particle and a non-particle, which is where all this is going. That is where this is going. The homework, so the homework is, I can't say that's fun. I think it would be very fun to discuss. The homework is not meant to be hard. It's like silly tasks that you do at your desk and then you write things about. Like basically you can do sometimes this homework that I just put in as homework 3. Sometimes we even do it together on the first day in class. Like it's, there's a lot of the questions don't have right or wrong answers as such. Well, I shouldn't exactly say that, but you can do homework 3 without any math in your background and without homework 1 or 2. So please do, and don't try to overthink why we're doing it. Don't try to see how it connects. Just do it for fun and be ready to discuss it when we come back Monday. Okay, this is a side note, but I just put in homework 3 in everybody's box. It is not hard to do. It would be a lot easier to do than homework 2 or 1, really. It's not very quantitative. But just please do it or do your best to understand it. And we're going to discuss it next week. And then you'll also understand better. I'll be able to talk about more why I put the children's story in the Google Stream. Okay. And again, the children's story is not required. That's just like material that's there. Homework 3 is required, but do homework 2 first, please. Blah, blah, blah. Okay. That all said, if that makes sense. I'm going back. Oh, yes. Yes. So what? Yes. What's in the chat is yes. And this is really important because 2 pi radians, has we're going to be dealing with 2 pi radians all the time from here on in math and physics. Like a cycle is 2 pi radians, and angular frequency is like 2 pi radians per second or 4 pi radians per second, or like. But there's problems with things like 2 pi radians. First of all, pi freaks people out, and second of all, radians freak people out, and we need to separate the two, the two freak out things. Excuse me. So the first thing is, if I'm drumming into our skulls that 2 pi radians from here on just means a cycle, like a 2 pi radians, first of all, means a circle. But from here on into physics, that means a cycle. 2 pi radians is a cycle, just like it's like saying 12 feet equals an inch. No, it's not. It's like saying 12 inches equals a foot. Okay, 2 pi radians equals a cycle. But now, and wait, sorry, there's something in the chat I know. Oh, yeah, right. Oh, wait. Yeah. Sorry, what Gabrielle, which I'm not saying right, I'm still not saying, and Quasi just put in the chat like yes and yes, but it's like important. Yeah, I'm totally. I am intentionally changing a direct equal sign into an approximate equal sign, which is a really important thing to do in science. And it will. Some of you will like the minute you see an approximate sign, you're like, this is not science anymore, or something. No, au contraire, mon frère. It most certainly is. But what I want, but don't fuzz me out. Don't think, oh, now he's just making some sort of approximate point. No, I'm making a very precise point about approximations. Like what I want to say is, if you're digging that 2 pi radians just means go around the circle, okay? But yeah, pi is a number. Pi is a number. It might be a fun number, but it's a number. It's like 3.14. More to the point, it's like 3, okay? Yes, pi is a little bit more than 3, but it's a number. It's a little bit more than 3. And in fact, if you were measuring it on like a measuring stick, on a meter stick, you might not have a meter stick precise enough to catch the 0.1 or the 0.04 or the whatever. Like somewhere you're chopping off digits with pi. And I'm saying, to get perspective on things, let's get used to chopping off all the digits after the 3. Like pi is only a little bit more than 3. Really, it's like 3 1/10. That is a tiny bit more than 3. So first, and what is that 3? It represents the ratio of circumference to diameter of any circle in the world. Let's pause on that for a second. Like I know you've been hearing about pi since 7th grade. In some ways, pi is way cooler even than maybe you know, but in other ways, pi is so much more straightforward than like we sometimes think. Pi is just this. Pi is saying go to any tree in the forest. Go to young Luke, whatever. Go to any tree in the forest, to make sure you're a druid with a constitution of 7. No, go to any tree in the forest. Now I have to make a Pokemon joke. No, go to any tree in the forest. And the point is this. Look at the tree. I don't care how big it is or how small it is. You look at the tree. Take out some string from your pocket. First, take a string and go all the way around the tree, like exactly once, right? A string that goes around the tree back to where it begins. Take that string and then lay it on the ground. Now chop across the tree, like chop that tree in half. Go from one edge of the trunk of the tree to the other edge. Saw it in half and take your string and go across that diameter. Lay that string down on the ground, right? So now you're going to compare what it's like to go straight across this circle versus going all the way around the circle. It's like, what's the 2 ways you could get somewhere? Like going around a perfect curve or going across a perfect straight line. Well, the curve, you know where I'm going to say, but I want to say it anyway. That curve around the tree, that string is going to be a little bit more than 3 times longer than that string. Like the 3 that we mean by pi is literally the ratio of nya to nya, right? Like how much worse is it to go all the way around than to go straight across? Well, the answer is 3, regardless of the size of the circle. This is the nature of circles. This is the constancy of pi. Someone first had to conjecture this and then verify it. Hard to verify. Anyway, pi is just that concept, that the circumference is like 3 times bigger than the diameter. Or, the circumference is like 3 times bigger than the diameter, i.e. the circumference is about 6 times bigger than the radius. This is all that a radian is the amount bigger than some curve is to some corresponding straight line. Okay, we're saying that any circle, any tree in the forest, if you go all the way around it, that's going to be a length, that's going to be a distance, like that's going to be an amount of string that is a little bit more, but only a little bit more than 6 times going from the center out, like 6 times the radius. There are 1 radian is approximately a 1/6 of a circle. That's all, like, in other words, like approximately 60 degrees, if you want to think of that, a little bit less, because there's a little bit more than 6 radians in a circle. There's actually 6.28. I mean, this is the quasi conversation, and Gabriel or Gabriel in the chat, like, right, I'm rounding pi on purpose now to really emphasize, don't be intimidated by that Greek letter. And don't be intimidated by the fact that it's like infinite non-repeating decimals. All of that's interesting and cool when we want it to be, but has nothing to do with the, like, just understanding a circle. Pi is basically 3. 2 pi is basically 6. And it's not 6 meters and it's not 6 degrees. It's 6. 6 being the amount of time. Good. Thank you. Thank you for saying that. That's cool. Okay. So a radian literally is a section of a circle. It's like, just like a right angle is like 90 degrees, right? A rad is like a 1/4 of a circle. A radian is basically a 1/6 of a circle. It's all it is. And when we talk about radians per second, when we say 2 pi radians per second, we're saying basically 6 pi, we're saying basically 6 radians per second. We're saying 1 cycle per second. When we measure angular frequency, we're just measuring frequency. We're just measuring hertz, but we're just always off by a 1/6. We're just counting 1/6 as often as someone who counts full cycles. Right? A radian is a 1/6 of a circle. In fact, take this one step further to really, it's like, it's all that a radian is. It's a 1/6 of a circle. A radian, let me say that again. A radian, or even better, a 1/6 of a cycle. If you ever hear about radians, don't look for angles, don't look for V's, don't look for trig. If you hear radians, it's a 1/6 of a cycle. It's like a cycle, but only 1/6 this big. So 6 of them make a cycle. That's all we're saying, but it can really easily get lost, but that's all we're saying. And in fact, one last way to put what a radian is, okay, here's what a radian is. To really understand what a radian is, remember that the definition of angles measured in radians is simply ratio of arc length to radius, right? So it's basically just how much crust you get per specified pizza. That's all we're saying, right? And then like, the reason I'm saying all these different ways, yeah, that's funny. Me too. I know. I hear you. Right. Damn it now. Yeah. Right. Thank you. Oh my God, that's so distracting. I can't. I feel like I just watched like a Jamie Oliver show or something. So I'm saying all this because you know what happens to people. Pi is intimidating in its own way. Radians are intimidating in their own way. And then what happens is people get locked into this habit of thinking that radians can only be ever discussed with pi's. It's not like we can talk about 2 pi radian, right? Yeah, we can talk about 2 pi radians. Pizza Zoom party. It's like a Zardy. It's like a Zitza Zardy. It's a Zoom part. Okay. I mean, this is not called Zoom. Well, I can't wait till this is. That is funny. Okay, that's funny, right? And of course, we're not in school anymore, right? This is called school now. This is like school, Zoom school. All right. Anyway, God, I hate Zoom so much. But it can be really. People can. Thank you. People can really get in the habit of thinking that radians can only come in like multiples of pi. Like, and this really screws up people on exams, by the way. Like, we could ask questions like, how many radians is this or that? And people will end up thinking that they can only give answers that have pi's in them. Like, well, there's 1 pi radian or 2 pi radian. But no, you can have a radian. You don't have to have 6 radians. You don't have to have 2 pi radian. You can have a radian. In fact, what is 1 radian? Well, what I'm trying to say is it's a 1/6 of a circle. But let's be more specific. 1 radian means 1. Like, you can have 1 radian. You don't have to have 1 pi radian. 1 pi radian means 3 radians. Honestly, like, pi is just a number. I'm going to, it's a funny number, but it's a number. It's not even that funny, actually. But what 1 radian would be, well, 1 has to equal S over R, but how is 1 going to equal S over R unless S equals R, right? The only way you're going to get a fraction of equal to 1 is if the numerator and the denominator have to be the same. Hence, S must equal R, right? In other words, what's 1 radian? 1 radian is this, here's your pizza. Different color, sorry. No, sorry. Right, I know I drew this diagram over there before, but remember, like the theta. Oh, good Lord. Okay, here's theta, right? Now remember, theta is supposed to be arc length over radius. But if we're looking for 1 radian, we're looking for that theta such that the arc length is the same as the radius, right? What 1 radian would be the slice of pizza. 1 radian, like not 30 degrees, not 60 degrees, not 90 degrees, like a radian would be the slice of pizza for which its crust size, its arc length precisely equaled the radius, the edge of the slice of pizza, right? That's literally what 1 radian would be. And again, it would be that regardless of how big the pizza was, that's what 1 radian is. If radians are the ratio of S to R, of arc length to radius, then 1 radian is literally when they're equal, when arc length equals radius, right? Again, like about, which is going to be at about 1/6 of the circle. But when the arc length equals the radius, think about it, that means that this curve part here is exactly equal to that part, to that part. In other words, what like what I'm literally saying is if you want to pick, and I'm going to stop, I'm going to look in the chat in a second. I really probably am really going to stop. But if you really want to picture what, like a radian is easy to picture. Again, it's a measurement of an angle. So it's some portion of a circle. What portion of the circle is it? It's the portion of the circle that comes closest to looking like a freaking equilateral triangle. Oh, thank you. Good. Oh, I'm glad. Okay. And again, I'm going to catch up with all the chat in a second. But yeah, like if you, I don't care how big the pizza is. If you've got a slice that's like long and thin, so one edge is a lot longer than the crust, then that's a very small angle. Maybe it's 5 degrees, maybe it's 10 degrees. I don't know. In other words, it's like way less than a radian. But if you've got, and you can always find this in any circle you look at, if you cut a slice that is wide enough in the crust, that crust length is basically looks just like one edge. Now it's never going to look perfect because the crust is curved, right? And the edges are straight. So on the eye, you're never going to get a perfect equilateral triangle because like it's a triangle with one of the sides being a little curved. But the closest you can imagine to an equilateral triangle where that curved part, so where the slice is squat enough, like not long and thin, but like squat. As soon as you make it squat enough that it's as wide as it is long, that is a radian. That's what I'm saying. A radian is where the arc length, and what is that? It's a little bit more, sorry, a little bit less than a sixth, a little bit less than 60 degrees. It's about 57 degrees. You could do the unit conversion on your calculator. It's like, but that's what a radian is. A radian is a sixth of a circle. It's the equilateral triangle slice. That's what a radian is. It's about 57 degrees. Let me look in the chat. So if nothing else, just think of a radian as 60 degrees. Like that's really, it's just basically 60 degrees. But degrees are stupid. We can get into that or not. Wait, a little less than 60 degrees. All right, now let me look in the chat. Sorry. Oh, a lot in the chat. Oh, I'm scared. I'm actually totally scared. Okay, hold on. I always thought that. Ed zoomcation. That's funny. Okay. I always thought that. Wait, what? Wait, what did I, okay, whatever Ronnie always thought was good, I'm glad, oh. Yeah. Well, it's 2.3 inch, wait, 1 radian is 2.3 inches of pizza, wait. I don't know if that's a joke or not. It's funny if it is, if it's serious that 1 radian is 2.3 inches. Yeah, it's through 2.3 inches, like depending. I mean, I can't literally say that. The whole point is it depends on how big the whole pizza is, but it is a specific fraction of a pizza. It's a sixth of a pizza. I like the pizza. Okay, cool. Okay, 50, thank you, Cat, 57.2. All right, awesome. That goes on for the gibbons. Oh, okay, great. Fine. Wow, nice. All right, fair enough. All right, I like what Gabriel, then yes, then I agree with the copy. All right, I'm gonna say, I'm sorry. I really hate to, I already did it to Angel, but do I say Gabrielle?
You can
or do I
pronounce
say-
it any way you like.
Okay, fair enough. You're very kind. Yeah, okay, I will, all right, I appreciate it. Okay. Does it make sense what we're saying so far? Does anybody have any? Very good. Okay, very good. Okay. It is making me hungry too. Tico Baba. So can we, let's do a couple of super quick examples. And if we're good with these and we get them right, let's go home. I mean, let's just for conscience sake, we're gonna do a couple of quick, but if we could do them quick, we could end in 5 minutes as far as I'm concerned, I think, which would be kind of early, but let's just do an example to make sure. Wait, did you? You did? Maybe we won't do the example. We either will or won't. Let me just ask this. With Walters, when you were looking at these things, you use Lagerpro and all that. Was it like usual where you looked at more than one example and some did turn out to be harmonic and some did not? Or you looked at one example and found out it was harmonic?
The former.
Okay, thank you. Great. Okay, perfect. Well said, I might add. So when you saw some that were not harmonic, what made it clear that they were not, like, were they not cosines at all? Or were they cosines that, like what? Oh, okay, let me see. Okay, sorry. There were 3 examples. One was harmonic. Okay, so the ones that were not harmonic, could anybody either describe in English or show me a picture? So like the ones that were not harmonic, what was not harmonic about them?
One of them was a constant acceleration graph. And then the other was a constant velocity graph. I
Oh,
believe.
great. Okay, this totally does it. So you're comparing so you're actually looking at, got it. Okay, and that is, oh, and they were not cosine. Okay. Got it. Oh, and one, right, and one was the one that Skylar said, but that was the one that was harmonic, presumably the thing that Skylar sent, I assume. Oh, so wait, so how did Lagerpro? So the graphs that you got that were not harmonic, they were just made up for you. They weren't through Lagerpro. They were just like made up for you. Yes, or like the constant acceleration or the constant velocity. Oh, whoa, wait, oh, wait, oh, wait. Okay, and again, all right. I just want to make sure that I'm not. So you're saying. So wait, let me just, first of all, is anything that I said so far contradict anything? Is anything confusing between what I said and what you did with him? I know I asked that before, but just want to make sure, especially if I'm, all right, let me see. Oh, you made graphs using the, oh, okay. Oh, you video, okay, that's great. Okay, no, that helps a lot. Okay, no, that does clarify. But then the one thing I don't understand, maybe, you're saying, you guys are saying that, hold on one sec. Oh. So you're saying, okay, hold on, I got you.
I think we said that the screenshot that I sent was not simple harmonic because of the way it abruptly like stops and goes.
That is awesome. Totally. Thank you for saying that. Thank you for sending it, first of all. Second of all, thank you for saying that. That makes total sense. That is actually what I was kind of hoping was your point. I was actually about to share the screenshot and say that and hope that it was true. That makes total sense. That's great. Let me, where? I am going to explicate that to everybody. Hang on one second. That makes, yes, that's great. So in other words, okay, now, hold on. And again, I will keep the promise about letting us go. I believe I can do this. Okay, right. So this thing, I'm just reiterating exactly what was just said. And again, thank you very much for sharing it, Skyla. And yes, so you're saying this thing did not count as simple harmonic oscillation because of those peaks, those points of not those points that are not smooth. That's what you guys are saying, and I agree with that if that's what you're saying. And I'm looking at the chat. Sorry. But yes, the abrupt endings. Right. Okay. Great. So we're all on the same page. If that's the case. Okay, let's just do one super fast example right now. I really do. It's like a plug and chug. Let's do one just to make sure that we're all going to heaven, and then we will stop. But I do think we are. I mean, I think you are. So I'm going to unshare that now. But that was great. Thank you. And now I'm going to do that. Okay. Oops, sorry. Oh yeah, no, okay, that's good. Oh, sorry. Oh, sorry, just fast. Okay. Okay, we're gonna quit. I would like every. I don't want you to race or anything, but just try to either in private. Yeah, let's just say I'd like you to answer these four, this A through D right here. Given x equals 5, it's just like exercises, plugs and chugs. We're going to do this. We're going to check it, and we're going to go. So everybody put when you have answers to these, it's not a competition or race. You can be wrong and all that, but I just want to see if we're all cool. So when you have answers to these 4, please put them in the private chat. Let's just keep it totally private chat. Just when you've done, or if you have a question or you get stuck, just put it in the private chat. And we won't get into a whole discussion. I'm just going to wait till I've so basically when I have input from everybody, you'll either put in the chat some answers or you'll put in, I got stuck here, or I don't understand this or whatever. And then once I've got a bunch from everybody, I will just quickly give you the answers, try to say them, and we'll go home. Like I won't necessarily get into a big discussion with each person, but so just as fast as we can do this. So try to do what's here on the page and just try to, when you've done it, these 4, try to put your answers in the private chat or put surrenders in the private chat or questions or whatever. As soon as we get this, we're gone. It's not meant to be a trick. And it's only a race in that once I get something from everybody in the private chat, then we'll be out of here faster. But you're not racing each other. Okay, I'm going to shut up. And I'm even going to say also in the interest of time, not just anybody once you, well, yeah, once you put anything in the chat, you can wait till you have all 4 answers or you can just put 1 answer. But once each person has put anything in the chat for this, then I'm just going to say what I think the answers are. So I'm not going to say if you're right or wrong or anything. I'm just, but cool. Well, yeah, maybe I will, but. Okay, I got a bunch of responses. Very good. I'm going to start, like, I don't know if it was quite everybody and maybe people still working. I'm going to just slowly write out what I think the answers are to the, oh, cool. Awesome. I just saw that. That's great. Person in direct chat. Awesome. Yes. Oh, that's 2 people. Yes. Yes. All of them. Ah. Well, good. All right, you guys are rocking it. Now, this is great. Okay. I've gotten a bunch of answers to A. People are pressing on to B. I don't want to, I want to keep my promise not to keep you guys too long. So I'm not going to, so I'm going to slowly write out the answers on that. Like, keep going if you're still thinking. A couple of people I might have said nice, just saying nice that you put in something I might not be guaranteeing that your answer is right, but wait, what was it? Great. No, it looks like almost anything. Yes, what the message that just came in. Cool. I think you guys are getting it. I'm going to write my answers now. You, if they're okay with you, then we're going to go. If they're not, we're going to talk for a second, but yeah, good. And again, all of you, anything that you just put in here, you can totally write up, you know, to submit for the 50 points or the whatever points, the 75 points, blah, blah, blah. Like, it really is helping me a lot that you people do that. Please do keep doing that. But okay, so here's my answers. So we have x equals. Oh, and you know what? Before I, what does this mean? So I'm saying like. Right. So first of all, just how to read this equation of motion now, like from here on in, whatever's before the cosine is the amplitude, the initial, the maximum displacement, you know, in meters from equilibrium, and whatever's right before the t is angular frequency measured in radians per second. So now to answer the questions, which I totally forget what they were. So when it says at t equals 0, what does x equal? Well, right, it better be 5, right? The answer to A is 5. Like that's sort of what that 5 right there means. It's wherever it was at t equals 0. But to check that or why that all works is, you know, cosine of 0 is 1. So x equals cosine of 0, which means 5 times 1, right? So it's not a coincidence. X absolutely equals 5 meters. Or if this is, assuming this is a meter, for that first answer is 5. You didn't have to write meters. I didn't actually, it's 5 for the first answer, like you people wrote in the chat, which is great. Then B, sorry. So again, we have x equals 5 cosine. Okay, so then B was, I believe what is at, right? I believe B asked straight up, what is the standard frequency? I mean, how many cycles per second is this thing making? Well, what I'm trying to get everybody used to is, I mean, you can plug in, you can go like this, you know, back to the other page, but also you could just think logically. I'm trying to say, like, there's 2 pi radians per every cycle. This thing is cycling at a rate of pi over 2 radians per second. It means it's, I in my head, I'm saying it's doing 1/4 cycles per second, right? Technically, because it's 2 pi radians per cycle over pi over 2 radians. Like technically that this is what's going on, right? And then the pi's cancel. So what we get is that F equals 2 divided by 1 over 2, right? 2 divided by 1/2, which is the same thing as 2 multiplied by 2. So we get, oh no, wait, what, am I crazy? Wait, sorry. Wait, something did just happen. Wait, what did just happen? Oh, sorry. Oh, someone probably put this in the chat too. Sorry. I mean to say. Right. Sorry. All the same idea. Just flipped it. Sorry. I'm sure someone put this in the chat. So omega is. Right. So this is what's happening here. And I'm not saying you have to go through all this every time once you're used to. Should I just do it again? But right. So yeah, but what this means is if you're completing pi over 2 radians every second, that means you are completing a fourth of a cycle every second, because it takes 2 pi radians to do a full circle, right? So the answer to B is 1/4. There's nothing in the chat. Okay. No, it's totally cool. Don't apologize. Nothing about. Right. So it's 1/4 cycles per second is the answer to B, which we now call from now on a hertz. 1 cycle per second is called a hertz. So the answer to B is 1/4. Then C, it asks what's T, right? So it's literally saying, it's asking you to go like this. And what you get is 4 seconds, right? Literally, I mean, if this thing is doing 1/4 of a cycle every second, what is that? Oh, sorry. If it's doing 1/4 of a cycle every second, then it's taking 4 seconds to do a cycle, right? So T is, and so then finally, was there a final question? I forget what the final question was. So finally, oh yeah. At T equals, what did I say? At T equals, what did I say? Capital T over, right. So finally, I do this weird thing. I say at T equals T over 2, like, find X. Well, I'm saying when the variable, like lowercase t always means the variable time, and capital T means the constant period of time. Like T is amount of time for one cycle. Lowercase t is just any old time that we're looking at. So we're saying, how far is this thing when a half of a cycle has elapsed? That's what this means, right? In other words, we just found out that T equals 4 seconds. Right, so we're saying at T equals 2 seconds, what's X? So we can just plug in if we want. We could say X equals 5 cosine pi over 2T. So we plug. And the cosine of pi is -1, right? The cosine of pi, unit circle, go to the other side of the unit circle. Cosine of pi is -1. So we get -5 is what X is. And that's the answer to D. But if you think about it, my last thing I want to say is I feel like that makes sense. Like I almost could have seen that before I did all the math in a way, because I'm asking, where is the mass at halfway through the period? Like I plugged in that the period is 4 here, but I don't actually even need to know what the period is to understand this question. In halfway through the cycle, where is the object? Well, a cycle is there and back. So halfway through the cycle, it's all the way there at the amplitude position on the other side, -5. Like it stands to reason that we would get -5 when T equals a half cycle. That's definitely enough for today. Like that, if you guys, I think that's a lot. Oh, cool. And I see in the chats. Oh, awesome. And thank you, Melanie. That's awesome. Cool. So if that's at all clear, I think that's a lot. I'm just going to say, I'm saying goodbye. I will hang out in case there's any questions, but I'm good to go. If you guys are good to go, and if you're good to go, just like say goodbye before you leave. If you don't mind, just say goodbye, and I'll say goodbye, and then I'll just say until there's it. Thank you, Veronica. Okay, awesome. That's exactly what I meant. Thank you, Veronica. Okay, bye, Veronica. Bye, anybody and everybody is in it. Bye, guys. Thank you. Bye. Good night. Thank you. Bye. Goodbye. Thank you. Bye. Thank you.
Have a
Awesome.
good one, Professor.
Bye. Thank you so much. Bye. Thank you. 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 Okay. Awesome. Awesome. Awesome.